Hello and welcome to my talk called How Engineering Solves Scientific Questions. Thank you for coming. This question has been on my mind for a while because as a mechanical engineer originally, I've had all kinds of experiences in the industry, and a lot of my experiences have shaped my career direction. Because when I first graduated from Brunel University with my undergraduate degree, I then decided to do an engineering doctorate in computational fluid dynamics, as was said. And I decided to do that engineering doctorate in industry. So it was a PhD that was based within industry. So basically a glorified apprenticeship for advanced kind of research. And when I was in industry doing this doctorate, which took me 4.5 years, I really saw a lack of people that looked like me and very few women. And I just couldn't understand why that was. So one of the things I really wanted to do was tell people about engineering, about how cool it is and how fun it is, and just a really exciting industry and how anyone can be in the industry. So one of the ways that I pursued this desire to spread the word about engineering was through media, because it's the biggest platform, right? Television reaches so many people. So I must say, when I came out of my doctorate, I was very shy, very introverted, and so I had to build up communication skills, and it took me absolute years. You never would have seen me do this several years ago, that's for sure. But communication was really important, and learning to package engineering in an interesting way that was engaging for a wide audience was really important for communicating engineering. And one of the ways that I found, one of the sort of ways to communicate engineering was through storytelling and people's experiences. So I ended up writing a book called Engineers Making a Difference. So Engineers Making a Difference is a project that is very dear to my heart. It took many years for someone to actually back me on the idea of writing a book like this, because making a difference, what does that really mean? You know, for years before COVID and all these very kind of unusual experiences, no one really wanted to hear about the do-good side of engineering. So to convince anyone to back me on a book called Engineers Making a Difference wasn't easy. But eventually, Imperial College London and the Gatsby Foundation said, we will back you on writing this book. So my book contains 46 engineers across 12 different engineering sectors, from health to transportation, food, beyond our Earth, all these different areas of engineering. And I talk about their personal journeys into engineering, because even though I took a very academic route into engineering, that's not the only way into the industry. And there are many more exciting ways, technicianships, apprenticeships, that kind of thing. And it's been so inspiring hearing from lots of different engineers. So that book came out in March 2023, and it was donated to every single secondary state school in the country. So 16,000 copies went out for free. And the reason why Gatsby and Imperial College and I wanted to do that is because engineering is not taught in schools. So over my career, I've had to talk about this skills gap in engineering, the lack of diversity, all these kinds of problems we have in the industry. And yet it's not taught in schools. Like, that just made no sense to me. So this book aims to plug that gap, to introduce people to engineering at a young age, to show just how varied and diverse the industry is. And then this summer, I finished writing Scientists Making a Difference. It's in grey because we haven't yet chosen the front cover, the colour of it yet, and it's just been sent off to the printers. And when I was interviewing for Scientists Making a Difference, same concept, finding out about different scientists' journeys through technicianships and apprenticeships and university routes, it was not so easy to interview them because I must be an engineer through and through. I mean, if you look at my family tree, there are many engineers in the family. My dad's an engineer. It's probably the reason why I followed in his footsteps. And talking to scientists and finding out about their research, I kept wanting to ask them, so what's the solution? And it made me realize in writing Scientists Making a Difference that actually there's a clear distinction between engineers and scientists. So the distinction is that whenever we ask questions, engineers want to find a solution and an answer. And whenever scientists ask questions, they answer a question with more questions. So it's this kind of perpetual curiosity of scientists, whereas engineers just want to build something and make something and come up with an answer. So I've had to really, every time I was talking to scientists, I had to say, I had to sort of like not ask them, so what's the outcome of your research, and just let them enjoy experimentation and following their curiosity. So just out of interest, how many people would identify with being an engineer in the audience? Hands up. Okay. Few. How many people would identify as being scientists or scientifically inclined? Okay, I think that's more hands. Yeah, so more scientists in the audience than engineers. Well, that makes sense because here at the RI, we're in an institution that has 200 years of fantastic science talks. And it's quite intimidating doing a talk as an engineer in a space like this because the history of scientists that have spoken here is really impressive. I was looking at the roster of people that have been speaking over the years, and I picked out a few people that were my favorites. And actually, the 3 people or 4 people that I picked out all had something in common. And I'm sure all of the speakers here have had these same characteristics in common, which is that they all had this insatiable curiosity. And they all had this absolute wonder for the world around them and an awe for the way things work and really trying to understand how things work. So probably the person that is most iconic here, there's a museum downstairs of Michael Faraday. He was the first person to do the Christmas lectures here, which are really famous. And Michael Faraday was responsible for discovering the electric motor, the electric generator, the transformer, all of which form the foundation of our modern civilization. Because without these 3 components, we wouldn't have power grids, we just wouldn't have the kind of modern day living that we have today. I mean, I don't know about you, but I definitely cannot live without electricity. It would be really uncomfortable, put it that way. But Michael Faraday was one of these people that was very instinctive. He said, nothing is too wonderful to be true if it be consistent with the laws of nature. And I interpret that as meaning that he just really wanted to harmonize with nature. He wanted to find out all about nature and then build and invent things that sort of worked with nature, which is how he came up with these 3 components as well as many other things. And what's incredible about Michael Faraday is that he actually is self-taught. So he did an apprenticeship in bookbinding, and he, instead of bookbinding, he was actually reading the books that he was meant to be binding and taught himself physics and chemistry, and that's how he learnt the laws of nature, just through pure, sheer fascination for the world around him. Then Carl Sagan, an astronomer, again, someone, if you ever see his lectures on YouTube, he just brings astronomy to life. And I think that one of the key ways that he did that was to really personalize the universe. To me, as an engineer, I like nuts and bolts and just things that I can touch and build and make. Whereas he really brought something that is so unreachable, untouchable, almost to us. He personalized it. And he had a quote, "We are made of star stuff." And it's true. The ingredients in our human bodies are the same as the ingredients in stars. So it's kind of like this lovely mirror image of the universe and ourselves. He also looked at that photo of the pale blue dot that was taken by Voyager 1 in the year, it was the 14th of February, 1990, Voyager 1 took the picture of the pale blue dot. I don't know if you can see that little dot just right there. And he said of the pale blue dot, "Look again at that dot. That's here, that's home, that's us." And that was a picture of Earth from 3.7 billion miles away. And it was just, he really brought some compassion to science. He really loved astronomy. He was so humbled by the universe. And it wasn't just an intellectual pursuit when it came to science. He almost made science spiritual and human. And then another person that spoke here was David Attenborough. Now, I grew up with David Attenborough. I think there are very few people that haven't, because he is, a century old. And everyone, I was just thinking when I was writing this quote, I was just hearing him say it. And there's something about his voice. I wish I had a clip, actually, of his voice. It's so warm, and so you can just hear the absolute passion he has for nature. Now, he studied natural sciences at Cambridge, but he doesn't call himself a scientist. He calls himself a naturalist. And he said, "No one will protect what they don't care about, and no one will care about what they have never experienced." And he literally did bring nature into our lounges or wherever your TV is, and just, again, gave us that connection with our planet. I think everyone knows at least one clip from one of his series, whether it's Life on Earth, Blue Planet, all of these amazing documentaries. And he made us connect with different species and relate. And I just love his work, and he spoke here. Then, someone who I didn't actually know about is Susan Greenfield, a neuroscientist that did the first ever Christmas lectures presented by a woman in 1994. And she did a lecture called Journey to the Center of the Brain. And what she did was really personalize neuroscience. So she wanted people to feel at home inside their own minds, which was quite avant-garde for her time. She said, "Science isn't about knowing everything. It's about being excited by what we don't yet understand." Now, this is something that is not taught in schools. It's definitely not something that I was educated with, that getting things wrong, failure, is actually okay. We can learn a lot from failure. I really learned that in engineering. Anything that goes wrong, obviously we don't want things to go wrong, but anything that does go wrong, as long as we learn from it, they are not considered to be failures. And this idea of getting excited about what we don't know just fuels that curiosity that we should have as scientists. And sometimes I think the educational system is so stressed, they want to teach us so much, that there isn't really time or space for getting things wrong. And so I love the fact that Susan Greenfield really instilled that idea that, you can embrace uncertainty and you can embrace curiosity, and it's okay to admit when you don't know something. So over to you for a second, so I can have a bit of a break. I just want you to tell me what you think engineering is. Let's do a bit of data science. If you point your smartphones towards the QR code, you'll be able to participate in a poll. Just give me some ideas of what you think engineering is. Just some buzzwords, whatever springs to mind. You can't go wrong with this. I'm just really curious to see what you as an audience think engineering is. And we're going to switch to the Slido. So building, solving problems, problem solving, my favorite. Machines, making things. I think the larger the text, the more people have said it. So we're scaling up here. Lovely. Lovely, lovely. Physical solutions, yeah. Building something. Creativity, yes. Using maths and physics to fix problems, brilliant. Design, knowledge, difficult. Making ideas happen, thinking, systems, fantastic. I love the fact that problem solving is in big, bold letters. So problem solving, solving problems, perfect. So that just leads ingenuity, love that word. So I thought, I was hoping you would come up with this. Engineers are problem solvers, that's exactly what we are. And we want to create solutions. And when I first went into engineering as a mechanical engineer, I wanted to solve problems of fluid dynamics. And I'll explain more about my doctoral research later on. But I have always at my heart wanted to solve problems. And the problems that I try to solve today within engineering are very different from my fluid dynamics days, and I will also get onto that. But just have that thought that if we only had scientists, we would ask brilliant questions, we would have awe-inspiring theories, but we would have no way, without engineers, of observing, measuring, or managing the world. Engineers really build the instruments that scientists use. So engineers and scientists really have a collaborative partnership. We just can't have one without the other. So what questions have scientists been asking, and what engineering has come out of that? Now, I have a lot of slides looking at the engineering, but before I get onto those, the actual questions we've been asking have really evolved through the ages. So from ancient times to the Renaissance, we were asking basic questions like, what is this? How does this work? So we were asking things like, why does the sun rise and set? What are stars made of? How do plants grow? And how do we change cheap metals into expensive metals? You know, the first alchemists were really the first chemists. So we were asking really, really basic questions to try and understand more about the world around us. Then we move on to the Industrial Revolution and the Enlightenment age. And it then became about how do we apply all of this knowledge that we've acquired to really sort of improve our lifestyles, to measure nature, to describe nature, to improve life, to be industrious. So we were asking questions during that time of how do we harness steam to power machines? How do we generate electricity, and how do we use electricity? How can chemistry create new materials? So you can see that evolution of questions. Then we get to, so it was really about like mastering nature for human benefit and progress. Then we get to the 20th century, and then we kind of turn inwards. We start looking into the atom. We start probing the fundamental building blocks of life in our universe. And we start asking questions like, what exactly is inside the atom? How does DNA carry information? How can we control disease? And how can we harness energy? And so, as a result, engineers ended up building the most incredible machines. And I'm going to zip through a few of my favorites. It's a long list, and this was like my short list, because there's just so many amazing inventions. So, first one, the Hubble Space Telescope. Let me tell you a few facts about this amazing piece of engineering, right? So, it has worked for 3 decades in one of the most harshest environments of Earth's orbit. It's orbiting at a speed of 17,000 miles per hour. And its job is to capture images of the galaxy, which are billions of light years away. It's got a 2.4 meter main mirror, which is polished to the utmost incredible accuracy, because any flaws would just skew all of the images that are coming back to Earth. But it's a telescope that was built to be serviced by astronauts. So it was sent out knowing that we were going to have to send astronauts up to it to tinker with it, change different parts of it, like the gyroscopes, the computers, the cameras, and even the power systems. I mean, over 30 years, technology has really changed. And so astronauts have been updating it over time. And in that time, it has had to withstand extreme temperature swings from minus 150 degrees C all the way up to 120 degrees C. And that's every 90 minutes as it whizzes through from sunlight into Earth's shadow. So the amount of mechanical stress that's on the Hubble Space Telescope, and it's still functioning really well. In fact, what it can do is lock onto a target and stay steady to within 0.007 arc seconds, which translated means that it can fix on, say, a coin that is 200 miles away. That's how accurate it can take these pictures. It's been orbiting, it's done 35,000 orbits. That's 1.5 billion miles of traveling. And its original computer had less power in it than our smartphones. So this is one impressive machine. It's inspired so many other technologies here on Earth. So because of the Hubble Space Telescope, we now have better cameras. Obviously, I hope so. If it can do all that out in space, we now have better cameras here on Earth, better imaging devices, better medical technologies, navigation, robotics, electronics, you name it, materials, all of that has been inspired by trying to build this telescope. And as a result of Hubble being out there, it has helped us calculate the Hubble constant, which confirms that the universe is about 13.8 billion years old. So it's brought us that information. There's also the James Webb Space Telescope, which has been built completely differently. First of all, it's got a sun shield on it that is 6.5 meters of foldable mirror, and that's basically the size of a tennis court, right? But it wasn't built to be serviced. So once it was sent out 1.5 million kilometers away from Earth and subjected to near absolute zero temperatures, it just had to stay there and it just had to function. And there are hundreds of moving parts, ultra-sensitive infrared instruments. I mean, this is precision engineering at its best. Now, Hubble is the eyes on our universe, and it actually works in the visible part of the electromagnetic spectrum. So pretty much everything we can see with our own eyes, the Hubble Space Telescope can see. But the James Webb Telescope is actually more of a time machine. So it can peer deep into space and go further back in time than any telescope before it. And it really reveals how the first stars and galaxies were formed. And it works on infrared, so a different kind of technology. The next amazing feat of engineering is the Large Hadron Collider, so CERN, which is based in Geneva. It's 27 kilometers of track where we accelerate particles. I'm sure you've all heard of it, right? It's probably one of the most complex machines we have ever built so far. And it's designed to accelerate particles to 99.99, lots of nines, of the speed of light. And, essentially what it does is it smashes atoms together. And if, two cars were smashed together, all the bits would fall out on the collision. And scientists want to look at all the bits and try and find what atoms are made of. And as a result of CERN, we discovered the Higgs boson, which is a particle that basically confirms how particles gain mass. So some people call it the God particle. And I'll actually let you into a story. I went to CERN as part of the promotion of Engineers Making a Difference, that book that I was telling you about. Let me give you a little sneak peek of the video that I made. We're here at CERN, and I cannot tell you how excited I am. I'm going to be meeting Jamie Pinnell today, and he's going to be telling me how engineering meets physics. We're going to be going to Atlas, an experiment that happens. I just can't wait. So this is on YouTube. And you're free to access this video. But the reason I want to tell you about this is because when I got the opportunity to go to CERN, I felt a bit guilty because I was going to interview an apprentice engineer at CERN. And the reason why I felt guilty is because I've always had in my head, I don't know how this got in my head, but I've always considered CERN to be a place for Nobel Prize-winning physicists and physics and physicists and physics. And I was like, I'm going there because of engineering. This is really, I don't know, I feel a bit guilty about this. And when I got there, I was expecting to see all these people with big brains walking around, like all these eminent scientists. And I did see that. But when I talked to Jamie Pinnell, who's doing an apprenticeship at CERN, and when I saw his passion for how he maintains Atlas and all the other engineers that put their life and soul into making these incredible instruments, I was humbled. And when I talked to physicists at CERN, they said, you know what? We have all these amazing ideas of the experiments we want to do, the questions we want to ask, the theories we come up with, but none of this would be possible if it wasn't for the engineers. Engineers are what make CERN. And you know what? All those guilty feelings of going to CERN under the guise of engineering just melted away because it's true. What they have built there is absolutely astonishing, and it's all down to the engineers. And again, it's about collaboration because the scientists will say, we really need an experiment that does this. Can you go and build it for us? And then the engineers go off and design and build and test and iterate, all the things that engineers are taught to do. So CERN really is a collaboration between engineers and scientists. Another great feat of engineering is the human genome sequencer. So biology is really not my wheelhouse, but it's a feat of engineering in the sense that it reveals the deepest secrets of life. It works using a combination of microfluidics, lasers, robotics, powerful computing to turn biology into high-speed, high-precision engineering. Now, they don't look very interesting, but as a result of machines like this, we are able to understand the genetic blueprint, what our DNA reveals, what the coding in DNA reveals. I mean, it's really given us a detailed map of the human body as a result of working very closely with the Human Genome Project. And it's really designed to decode 3 million base pairs of human DNA. There's also MRI and CT scanners, again, using physics, magnetism to see inside the human body. It's allowed us to answer questions about anatomy, disease, how the brain functions, all in non-invasive ways. And it's revolutionized medical diagnostics and even surgery. Then there's nuclear fusion. We haven't quite cracked it, but we are certainly closer than we've ever been to recreating what happens on the sun here on Earth. Think about that. What happens on the sun requires a huge amount of gravity, temperature, pressure, loads of helium, fusing together, hydrogen, like all these ingredients, and we're trying to do that. What happens out there on the sun, here on Earth, that's nuclear fusion. And there have been incredible attempts to build tokamaks, create plasma, and, I was at First Light Fusion in Oxford, a company that basically has been inspired by the punching crab, because apparently the punching crab punches at certain pressure and creates a spark with their punch, and that spark blinds whoever the creatures they're trying to protect themselves against. And an engineer learned about the punching crab and this incredible force at which it punches and creates this plasma and thought, that's nuclear fusion. And so basically recreated the conditions of the punching crab at the depths of the sea, pressure, temperature, all these things. And it's trying to create nuclear fusion that way. But there's also ITER, an experiment in nuclear fusion. And we're almost there. We're almost there. Then there's the deep sea submersible, Alvin. So Alvin can take a few passengers, and you can be down at depths of 4,500 meters, which is 14,800 feet. Some planes don't even fly at that. So Alvin can go to incredible depths of the ocean. Normally, with something like that, it would crush. So the amount of engineering that is involved in just keeping everything safe and self-contained. You can be down there in a dive for 6 to 10 hours, and you've got emergency life support supplies. Should something go wrong, people could sustain themselves for 72 hours at those depths. But the engineering involved to actually create that is astonishing. It's got robotic arms, it's got cameras, it's got sensors, and it can hover over hydrothermal vents and shipwrecks and deep-sea trenches. It really reveals so much about our planet, and it's incredible to know that we actually know more about Mars and the Moon than we do our own oceans. So pieces of engineering like this are crucial for understanding our planet. Then we have Earth-observing satellites. So these really are our eyes on our planet. And, at this time of incredible climatic changes, it's so important to just keep an eye on the way things are changing, monitoring natural disasters, earthquakes, and floods. I was recently in Santorini, and, there was news earlier this year about how, there were earthquake risks. And put it this way, these satellites and providing data really calm me down, because they monitor our planet. They look at data, any sort of warnings about earthquakes and things like that is supplied by technology like this. And the information we have about upcoming earthquake risks and things like that is the best we will ever know for now. So the technology that has been developed is the best of our ability. And so hopefully we can still, develop these technologies. I actually emailed, when I was in Santorini, I emailed an earthquake engineer just saying, am I safe here? Because, I wasn't quite sure. And thanks to his knowledge, he was like, don't worry, it's fine. There were a few tremors earlier on in the year, but things have subsided now. And so you're safe, don't worry. So as a result of, these kinds of technologies like the International Space Station, satellites, all these things, we have developed water purification systems, air filtration systems, spacesuits for the International Space Station have informed us about creating firefighting suits, hazardous material suits, sports, outdoor gear, insulation layers, medical prosthetics, mobility devices. Has anyone seen the exoskeletons? Where people can actually, those who are in wheelchairs can actually wear exoskeletons that support their body and allow them to walk. Incredible technologies as a result of space technological advancements. And again, with missions like the Apollo and Artemis, like material science, cars, airplanes, protective gear, GPS, weather forecasting, communications, Earth imaging, robotics. The list goes on as a result of all of these incredible technologies. So just a bit more about my own engineering journey. So as I said earlier, I'm a mechanical engineer. And with mechanical engineering, you are very much concerned with machine development, whether that's planes, trains, automobiles, thermodynamics. Mechanical engineers learn about how fridges work, ventilation systems. And my dad is a building services engineer, so I kind of had to / wanted to go into building services engineering, following the footsteps of my dad. And actually, I must say that during my mechanical engineering days, I really loved the fact that mathematical equations could predict what is normally invisible to us. It's called computational fluid dynamics. Fluids are anything that flow, gases and liquids, but most fluids are invisible to us. So looking at how air moves is not easy because you just can't see it. But on a computer screen, using algorithms and all of the knowledge of Bernoulli, his equations on temperature and pressure and conservation of mass and momentum, he came up with algorithms that we then use for computer algorithms to simulate how gases and liquids flow. So that's what my PhD was on. It was all about looking at how air behaves in buildings. Now, granted, this is not the sexiest of fluid dynamics, looking at air in buildings. Fluid dynamics can also be used to model Formula One cars, way more sexy, or could be used to look at how air travels over the wings of an aircraft. And it's so useful to engineers because by understanding fluid dynamics, you can optimize design. You can therefore reduce the amount of fuel you're using, particularly when it comes to aircraft. And it's just a really great tool for engineers. And when I was doing my doctorate, bearing in mind that my doctorate took me 4.5 years, and I finished in 2004. So this is 21 years ago. I am that old. So computational fluid dynamics isn't what it is today. Back then, 21 years ago, CFD, computational fluid dynamics, was basically a tool where you could take a snapshot image. So it was like taking a photo of the fluid dynamics in a room. So this photo on the side here is showing the fluid dynamics in an office space. And photos are good and useful, but they're not really realistic. What you want is something dynamic. This is a steady state analysis. This is a static analysis, a photo. And engineers really want to know how things change with time. What happens if more people enter the office? What happens if someone opens a window? What happens if they switch the ventilation up or down? How does that change the fluid dynamics in a room? And this is all to optimize the fluid dynamics in a space. So my PhD was looking at how do we solve all of those complicated Bernoulli equations on a computer where you have to look at various aspects, the scientific questions, like how do you solve fluid dynamic equations over building material? It takes so long for heat to move through a building envelope, but it's almost instantaneous to calculate how air behaves in a space. So one is a heavy material, one is instantaneous reaction. Air is an instantaneous reaction. Building envelopes take a long time. Trying to compute equations over those two materials is computationally demanding. And 21 years ago, computers were not like how they are today. And so I was kind of looking at developing the equations. I came up with this theory of freeze flow, where you freeze the equations over the air and you keep calculating over the building envelope, and then you exchange information. I basically did what AI can do like this. So yeah, I was completely replaced by AI, but back then it was useful. The thing is, CFD used in buildings wasn't particularly fashionable. It was an expensive tool, and so it wasn't really used much. And then COVID happened. So COVID, I mean, this is a little video of the dynamic simulations. So, air is coming out of the vents. There are all kinds of fluid patterns going on because of various things happening in the room. Don't forget, you've also got the added complication of the sun traveling over a building, and that can change the thermal conditions in a space. So there were so many scientific questions that were being asked. And so COVID happened. Should I tell you my COVID story now? Yes, okay, I will. So COVID happened, and suddenly CFD in buildings became really fashionable. So it was like the research that I did was kind of dormant for 20-something years, and then, or slightly less than 20 years. And then it became really fashionable because the airflow in buildings would transport COVID particles, and everyone wanted to know the fluid dynamics in enclosed spaces. So what I was working on became really useful, and actually so useful that that's how we got our social distancing measures. That's how we had to redesign the air conditioning systems in certain situations, like on an airplane or in various... Okay, I'll skip to a few slides later. Let me show you. So I did the aerodynamics of COVID, social distancing. This was a film I did for TV. I also was looking at the fluid dynamics in a plane, which is the video next to it. And then a film that I found really fascinating to make was the fluid dynamics around an orchestra. Because during the time of COVID, we couldn't go to theatres like this. We were too close together. We had to socially distance. And I never thought about this until I made this film for television. But there's a lot of fluid dynamics happening when musicians are playing instruments. So because musicians were desperate to get back into auditoriums like this one and play their instruments together as an orchestra again, they decided to do a fluid dynamics analysis of playing their instruments. So there were sensors attached to trombones and trumpets and clarinets and flutes. And they managed to reconfigure orchestras so that they were not breathing in each other's out-breaths, basically. And they could also keep the audience of the orchestra at a safe distance. They could determine the ventilation into a space. And they basically, thanks to fluid dynamics, were able to play their instruments again in front of an audience during COVID. So CFD has been useful. Now, one of the reasons why I really wanted to look at CFD in buildings was because of something called sick building syndrome. Has anyone ever heard of this, sick building syndrome? It's a syndrome that basically strikes people who tend to work in high-rise buildings, because if you think about it, they're just a kind of sandwich of floors, and engineers have to design ventilation systems so that the air conditioning is constantly refreshing the air on every floor. And as a building services engineer, there's something like, I can't remember how many changes per hour, but you have to have a certain number of air changes an hour for us to all be healthy. And in some high-rise buildings, the ventilation systems don't reach certain corners and pockets of a space, just because the ventilation system hasn't quite been designed well enough. And you get something called sick building syndrome, where pockets of air are stagnant, not being refreshed by the air conditioning system. Let's just say it's a pocket over here. And it's air that is stale, it's moist, it's warm, which is a perfect breeding ground for bacteria. And bacteria can grow and multiply in these warm, moist spaces. And people that work in high-rise offices can breathe in that toxic air and get something called sick building syndrome, which can cause days off sick, make you feel a bit flu-y. And it's actually a real thing. I mean, we do spend something like 90% of our time, I can get the stats for you, something like 21 and a half hours per day we spend in buildings. So it's really important to have good ventilation, because otherwise you can get something called sick building syndrome. And I'm not really making this up. There was something called the curse of the pharaohs. And it was actually this myth that the myth was that the person that opened the door of the tomb of Tutankhamun died because of the curse of the pharaohs. So let me backtrack. Tutankhamun's tomb was shut over 3,000 years ago. So Tutankhamun was mummified, put in his tomb, door was shut for over 3,000 years. Again, no ventilation, perfect breeding ground for bacteria where it's warm and moist and bacteria could just grow and multiply. And then someone came along called Lord Carnarvon, thank you. And he funded someone called Howard Carter, who went on an expedition to discover the tomb back in November 1922. Now, myth had it that these people died very suddenly and unexpectedly after the tomb doors were open. Was this the curse of the pharaohs? Or was it a lack of fluid dynamics in the tomb? Well, thanks to simulations, we now know that it was a lack of fluid dynamics and not a curse. And anyway, the papers really wanted to sensationalize the whole story, so they were winning out of that as well. I was asking all these questions. A lot of scientific questions were asked in order for me to develop my CFD research to make CFD better and more advanced. But that's not the only route to engineer things. I'm a member of the Blue Plaques Committee, and I've been doing a lot of blue plaques on my social media, on Instagram, because I love hearing about engineers who had some connection to London and English heritage sites within London, and finding out about their journeys into engineering. And these three men are all engineers that made an absolutely significant contribution to engineering, and none of them went to university. They are people who left school at 14. I'm not encouraging this, by the way. I'm just saying that if you really do want to engineer things and you really have a curiosity for inventing and finding solutions, you don't have to go to university to do that. So Oliver Heaviside was a physicist and mathematician. He revolutionized telecommunication. He left school at 16, was largely self-taught, and just loved independent study. And we are living in an era where we can do a lot of independent study thanks to social media. George Livesey was an engineer and industrialist and became chairman of the South Metropolitan Gas Company. He gained work experience in an engineering gas industry job and never went to university either. And then Tommy Flowers was an electrical engineer, and he helped to design and build Colossus, which is the world's first programmable electronic digital computer. And that Colossus helped to decipher German codes during World War II. Flowers left school at 14, again was largely self-taught, and gained practical experience through apprenticeships. Now, I know apprenticeships has a bit of a stigma attached. I know that my dad was like, don't do an apprenticeship, you've got to go to university, you've got to do everything the right way. And yeah, but honestly, if you really want a job in engineering, it's so important to get work experience, and apprenticeships is a great way of doing that. Earn while you learn. I'm all for it. Last week, because I'm a trustee of the Global Communications Museum in Cornwall, in Port Curnow, and last week I gave a talk on the women in war. This is really a talk about women who had no intention of being engineers. They basically rolled their sleeves up and got on with things, because at the time of war, many of the men were sent off to fight, leaving the women behind. And these women were doing other jobs, like they were upholsterers and secretaries and all the typical jobs that were expected of women during that time. And these four women have incredible stories of contributing to Bletchley Park, where German messages were decoded, deciphered, thanks to Colossus, and then also, there was the bomb. There were many, many different mechanisms that we developed to try and decode these messages. Avis Joan Hearn was someone who was a radar operator. And again, she had to really understand the transmitters, the receivers, all the instrumentation that was used to basically ensure that she could send messages to our RAF pilots. Now, during the Battle of Britain, the Nazi German warplane, the Battle of Britain was an airborne battle. So it was only fought by air. And there were about 3 to 4 Nazi German planes to 1 RAF plane. That was roughly the ratio. So it was really unlikely that we were going to win this battle. But thanks to getting messages from the radar stations to the pilots, we were able to win that war purely on strategy. And it was down to women like Avis Joan Hearn who really mucked in and helped get those messages across. And then Florence Attridge, she worked in the Marconi factory. So she was busy winding coils around iron cores to make the essential components for radios. Marconi is a famous radio company. So absolutely key jobs when it came to the war efforts. So the questions that we ask today are really different. Thanks to AI, thanks to quantum, thanks to nuclear fusion and generating power in very different ways. And so now we're in an era where I think we're asking questions about how do we do science responsibly? What does it mean to be human? Because yes, my job, if my job's very predictable and repetitive, could be replaced by AI, but it allows me to be much more human, more creative, more ingenious. So the questions we're asking as engineers today are very, very different. I think we all agree that we're living in an extremely unstable, uncertain time, not just politically, but also climatically, if that's even a word. So we really do have to ask questions differently and really have the benefit of society at the heart of our questions. If scientists can do that, then this will inform engineers to engineer differently. And I really believe in engineering being put to use for the greater good. And so today we're coming up with engineering solutions like smart cities, smart infrastructure, monitoring and restoration, sustainability, circular and adaptive technology. So really trying to be, conscious of what we recycle, what we repurpose, all of that kind of engineering thinking, rather than building and making machines that work. It's about thinking on a more humanitarian scale and just being more conscious. So that brings me on to really the problem I'm trying to solve today in engineering. And it's some people might say it's a bit woo-woo, a bit hippie, but I think it's absolutely essential for the future of engineering. And that's really looking at the problem of reputation or the intention of engineers, because my experience has been that not many people are choosing engineering. I don't know what it is about engineering in the UK, but for some reason, the reputation of engineers is so different to other countries. Engineers in this country are not seen as society's secret superheroes. And I don't understand why that is, because I really fundamentally believe that engineers really are superheroes. I mean, during COVID, yes, doctors and nurses were essential, but engineers are the ones that erected hospitals in no time at all, built ventilators, had to think on their feet, came up with refrigeration solutions for our vaccines, came up with the vaccine, so many solutions that they had to think on the spot for. And so I think we have to improve the reputation of our engineers. And maybe that's down to intention. We have to want to do good, and we have to think in a much more agile way. We have to not feel bad about being caring towards our society, and we have to engineer for good. So engineers are not just people in bowler hats walking with a cane, like Isambard Kingdom Brunel, the man who my university, where I'm pro-chancellor, is named after, Brunel University. They're not just people in hard hats, although engineers do often wear hard hats and walk around with blueprints. They are engineers that look like this, and there are 46 of them in my book, and they all just do not look like the stereotypical engineers. So there are many unconventional routes into engineering: technicianships, apprenticeships, work experience. I've covered this, I think, already. And if any of you are engineers in the audience, and I know there are a few, think about communicating your passion more, because one of the reasons why science is so much more popular than engineering is because of places like this, where scientists can communicate their passion. And I think engineers need to really own their responsibility for communicating their passion for engineering. People trust engineers. There have been surveys about how much trust engineers have from the public. But what we need is to really improve our status in society and to improve our visibility And we can do that in the age of social media. We can really communicate what it is that we do and how we all can look different. There is diversity in engineering. We just need to speak up about it. So let's all work collectively to really take a look at the wonder and awe of engineering. Keep up your curiosity about what it is that engineers do. I hope I've given you an insight into how incredible engineers have been in aiding the science. I've got a series on YouTube called Crash Course Engineering, which you can all access for free, and just learn a bit more about engineering, and let's give engineering a bit more airtime, or at least as much airtime as we do scientists. So thank you all for listening, and I look forward to hearing your questions now. Thank you.